Assalamu alaikum and hello dear friends. Today I am going to start the second video of the series how to solve a beam or how to find the reactions of the beam. In previous video we have solved a simply supported beam carrying only point load. In this video lecture we are going to solve a simply supported beam carrying a uniformly distributed load. So watch the video full, and if you have any question regarding the topic, please write it in the comment box. I will try to answer all of your questions. So without wasting any time, let's start the topic.
Today we are going to find the reaction of a simply supported beam carrying a uniformly distributed load over its entire length. This is a simply supported beam carrying a uniformly distributed load over its entire length. The magnitude of this load is 5 kPa and the length of the beam is 10 feet. This beam is supported by a hinge at support A and supported by a roller at B. We can see that this is a statically determined beam having only one vertical direction at each support. These vertical directions are represented by RA and RB respectively. Now to find these vertical direction RA and RB, we have to use the equation of equilibrium that are sum of all horizontal forces is equal to 0, sum of all vertical forces is equal to 0, and sum of all moments about z direction is equal to 0. We can see that in this beam there is no inclined or horizontal load, so we have no need of sum of all horizontal forces is equal to 0. So we will use the two equations, sum of all vertical forces is equal to 0 and sum of all moment about z axis is equal to 0. Now to find the reaction RA and RB, we have to take the moment about either at A or either at B equal to 0. If we want to find the reaction RA, we have to take sum of all moment equal to 0 at B, and if we want to find RB first, we have to take sum of all moment about A equal to 0. We want to first find RA, so I have taken sum of all moment about Z axis is equal to 0 at B. A direction for a positive moments, I have given clockwise moment positive direction. You can also give an anti-clockwise moment a positive sign, but you have to consider it over entire problem. Now to find the reaction RA, we have to determine the moments of all forces acting on this beam at B. To find the moment of a force or a load, we have to multiply the magnitude of a load into its perpendicular distance from the load to the point at which the moment is taken, and this perpendicular distance is known as moment arm. Now starting from the left side, the first load acting is RA. The moment of RA will be the magnitude of RA, which we have to find, and its perpendicular distance from A to B, which is 10 feet. So I had multiplied RA by 10. 10 is the moment arm of the reaction RA, and I have given it a positive sign because RA is producing clockwise moment about B. The second load acting on this beam is 5 kPa, which is distributed load. The moment of this distributed load about B can be found by multiplying the resultant or the total magnitude of this load with the moment arm of this load. The resultant load of this load will be acting on the center of this load, as the load is applied on the entire length, so the center of the load will be coinciding with the center of the beam. Now to find the magnitude of this resultant, we have to multiply the magnitude of load per unit length into the total length of the load. The magnitude of this load is 5 kPa and the length of the beam is 10 feet. So the resultant load will be 50 kF, and the moment arm of this load will be this distance, which can be found by dividing the length of the load by 2, which is 10 divided by 2. So by simplifying the calculation, we will get 10RA minus 250. We have given negative sign to this moment because this distributed load is producing anti-clockwise moment at about B. Now 10RA minus 250 is equal to 0. Shifting 250 to the other side of the equation, we will get 10RA is equal to 250. Solving this equation, we will get RA is equal to 25 kips. So we have determined the first reaction RA, that is 25 kips. Now to find the other reaction RB, we have to use the second equation of equilibrium, that is sum of all vertical forces equal to 0. Here we have also to specify positive direction of the load. Here I have taken upward acting load positive and downward acting load negative. Starting from point A, we have three loads acting on this beam, that are RA, RB and the distributed load, which is 5 kips. So here we have RA, the distributed load, and RB. You can see that RA is positive because it is acting upward, RB is also positive because it is acting upward, and the distributed load is negative sign because it is acting downward. We have already determined the value of RA, so we will put 25 in the place of RA minus 50 plus RB equal to 0. By simplifying this equation, minus 25 plus RB is equal to 0. Now shifting this 25 to the other side of the equation, we will get RB equal to 25 kips. So we have solved the beam and find both the reaction of the beam, that are RA is equal to 25 kips and RB is equal to 25 kips. Here both reactions are same because the beam is symmetrical. Now to check that we have determined these reaction correctly, we can use this simple trick that sum of all upward forces must be equal to sum of all downward forces. You can see that there are two upward forces that are 25 kips plus 25 kips, and there is a distributed load which is acting downward, and the magnitude of this distributed load will be equal to 5 be 10. So from this side 25 plus 25 is equal to 50, and from this side 10 into multiplied by 5 equal to 50. So we have getting the same value at both sides. It means that we have calculated the reactions correctly.
That's all for the day. Thank you very much for watching the video. I hope that you have learned all these things. If you have any question, write it in the comment box. I will try to answer all of your questions. If you are visiting the channel for the first time, please subscribe the channel and do not forget to like, comment and share the video. For more updated videos, please keep in touch.